Hello everybody, welcome back to my channel. So today, as you can probably see from my screen, it's quite late, so sorry if I whisper and stuff. But today I'm gonna just be showing you like how to use a data set and like kind of the process or my thought process of what I do when I run a regression, starting right from scratch. So yeah, hopefully you find this video informative and the other people watching on my course. Good luck with your project, I guess. But yeah, without further ado, let's get started. Okay, so I'm just gonna start off by opening a dataset. This is a random dataset that I have found off online just because the one that our university's coursework uses is like, well, it said in the briefing that it's like confidential or like it shouldn't be used for third party usage. So just to be on the safe side, I have found something random. So let's go in my downloads. This was from my other video, but anyway, it's called London Data. I have never seen this data set in my life. I've never used it before. This is literally the first time I've ever seen it. But okay, so what you usually want to start off doing is if it's like a widespread data. Let's say for example, there's a lot of categories that you want to be focusing on. So let's say you want to split up your data between like your data analysis between male and females. If you want to just exclusively look at data within males and females, what you would typically do is basically you can tab it, so it'll be like, let's see what's let's see. Okay, so we don't actually have something that's a categorical or a dummy variable in this case, but if you were, you could do like, I don't know, tab, and then you just put your variable name in there like that, and it'll come up with like some stuff, and then you could type in tab variable no, or it's like no like that, and that just shows you the number on the list. So number on this is null, and then you can basically say drop variable name and then put in a number. So let's say like females is 2, we just look at males, you just put in 2, and then you can basically save that data set as like something like an appropriate a name like males or an appropriate name like females, and then run your analysis like that. So assuming you know how to do that, we can just basically like run a regression. So I've never looked at this data set before, but let's say we want to see, I don't know, like how income is affected by the number of children. Let's just run like a really simple regression. So what you would write is, hopefully I'll put it up on screen if not, but you'd be basically running your dependent variable equals to your estimated coefficient multiplied by your x explanatory variable or your independent variable, because we only have one in this case. So the command for that would just be regress, or I just type in reg, and then you can just come over to the variable section, and you always put your y first because that's the order that Stata would put it in. So if I put like w food first, let's say for example I just did that, then Stata would assume that w food is our dependent variable, but we want it to be income, and we said number of children, so you just write it as that. So you put your y first, and then the x variables can be in any order, it doesn't actually matter. The estimated coefficients won't actually change, so you just press enter, and then you see this weird interface, which is quite scary at first. To be honest, when I first did Stata, I was like, what is this? But yeah, basically what we have here is a menu of things, shall we say. So when you're looking for the estimated coefficient, oh, that was my chair, sorry. You just look at the coefficient section. So you have your income, which is your dependent variable, and then your independent variable, NK, which stands for number of children, as we can see in the label variable section. And essentially what we can say here is that our simple linear regression model, because we only have one variable, predicts that if you increase the number of children by 1, then it is estimated that the income of the household is to increase by 3.18. Let's just assume it's in thousands, so we'll times it by 1,000, so around 3,182, let's say, pounds, right? So basically what you want to do with estimating coefficients is remember your 4 rules. So off the top of my head, it's the linear to linear, which is basically where it just stays the same. So whatever you see here is whatever the actual value is. And then there's linear log, log linear, and log log. And those are essentially all the rules that you need to determine how you estimate a coefficient. You can probably search it up on Google. And if you're on my course, there's probably stuff on it in the lecture notes. But basically, what you want to say is the model predicts, because it's not like a full accurate estimation. It's just kind of like it's around what it is, because sometimes there are other variables called confounding variables that might actually affect our regression, but they're obviously not included because they're in our error term. So yeah, we have to say that the model predicts that whatever our x variable, if it's increased by 1 unit, like the marginal unit, so we would say 1 unit, but here we know that NK stands for number of children. That's why I said adding one more child, or you can just say like an additional child, will have an effect on our dependent variable, which is income in this case. So you just have to be very careful of the wording. But once you start doing a few regressions, you can start to see how everything kind of adds up together. It's kind of like adding pieces of a puzzle together. That's basically it on the estimated coefficients. But there are also additional things. So personally, I didn't really look much into standard error. You have your t statistic here and your p-value. These are like the two main things that you should really look out for with estimated coefficients, because they kind of give you a guidance on how reliable they are on explaining their effect on the dependent variable. So kind of in layman terms, they show how much the x variable actually affects the y variable, because you don't want an x variable to be included in your regression when it's got nothing to do with the y variable. Let's say I don't know how many let's just say Ceteris paribus, how many mice, no, not how many mice, how many times you breathed air, let's say, how does that affect your income? Well, it's like, it doesn't really affect your income how much air you breathe in, like the volume of air you breathe in. So you don't want that type of variable to be in your regression. So these are what they're kind of like indicators, if you must. So you can look at the t-value, and depending on your significance level or your confidence interval, the point at where you reject your t-statistic depends on your t-value, which you can find on the student t-table, or you could just take the easy way out and look at the p-value, because let's say we had a 95% confidence level, which means we have a 5% significance level. This is assuming a one-tail test, by the way. So to find a significance level would be 1 minus the confidence level, which is where I got 5 from. You would basically say at the 5% significance level, if your p-value is less than 0.05, aka 5%, then you have enough evidence to reject the null hypothesis and accept the alternative hypothesis. Hopefully I'll put it on screen again, what I'm saying. But it basically means if you can reject the null hypothesis, which is equal to 0, that means that it has some degree of explanation to impacting your y variable. But if it's equal to 0, that means that there's like no correlation or no reason or no effect on y. So hopefully that made sense. But essentially, the smaller the p-value, the more reliable the coefficient. But what we have here is 0.322. That's pretty bad. Just like looking at it on itself without thinking of the broader context, that in itself is a bad indicator. So it suggests that the number of children actually doesn't affect income. Although there's a reason for this, and this is because we need to include more variables. So sometimes when you include more variables, depending on how much they impact on each other and on the y explanatory variable, this might actually change the coefficient and also its reliability. So you kind of have to play around with your regression sometimes. So we can also, make it a multilinear regression model, which essentially just means what we typed in earlier, plus, adding another variable in, let's say age, which stands for age of household head. And let's say we do budget share for alcohol. So WAUC. And we just pressed enter. And as you can see here, just looking at NK for the time being, the p-value actually went down and the estimated coefficient actually went up. And this is because we added more variables. So the more variables you add, the more it's gonna show a more accurate representation of the variables that affect your income. So just for learning purposes, we'll also look at the other ones. So suppose we look at age, and we have our estimated coefficient, which is 1.798, yada 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 yada. This basically says that the model suggests that if you increase the age of the household head by 1 year, then your income is estimated to increase by, we said, in thousands of units, so around £1,798. Pretty easy. And we can also say that it's quite reliable because this, by the way, this doesn't literally mean that the answer is 0. It just means that the p-value is very close to 0, because obviously you can only, Stata only outputs out 3 digits after the decimal place. So obviously there may, we don't know, but we just have to assume that there are numbers after the 0. So we can just say it's very close to 0 or a very small number, which means that even at the 1% significance level, we can reject the null hypothesis, which makes this a very reliable coefficient. So we can basically say that this is a good variable to represent income or the effect on income. And then again, it's the same for our WAUC, our budget share for alcohol, right? So that's essentially it. There are other things that you can consider, like for example, let's have a look. So in our original one with just income and number of children, we see that the R squared is 0.00006. Now that is kind of, think of it as the opposite of the p-value. So the smaller the R squared value, the worse it is, because the R squared is essentially the goodness of fit, or whatever it's called. And basically what it does is shows us how well our variables fit within our so-called best fit line. So imagine like a best fit line, and then imagine like your variables around it. If it's very close to that best fit line, then the R squared will be higher because it's shown that that relationship much better. But if it's very far away, I think that's the residuals value, then your R squared will be much lower. So we can see here that it's a 0.0006, but once we start including more variables, obviously that means that our variables are going to be closer to the best line fit, and it increases a little bit to 0.0537. So R squared is between 0 and 1, because it's basically calculated as a percentage. So if you times this by 100 up here, we have 0.06%, and then down here we have we have a 5.37%. So it's quite a big jump. And just an additional note, our adjusted R squared is the better version of the R squared, because it essentially has this like eliminating factor where, because every time you increase the number of variables you include in your regression, it will naturally increase the R-squared value because of the R-squared equation. But I won't get into too much detail about that because it should be quite obvious in the theory. But yeah, it essentially creates like this this like eliminating factor. So every time you increase n, that doesn't affect on your R-squared because it's like this like weighted balance which counters it. So that's that. And then just one last thing, if you want to include things such as non-linear relationships just to create a better representation within your model, there are multiple ways of doing it, but I'll show you two methods. So one method is, let's say that age has a non-linear relationship to income. So let's say at the beginning you have the higher your household head. So let's say, I don't know, if they're 34 and then to 36, that will increase. But then after they're 36, it'll start to diminish because, you know, of the backward bending supply curve, which suggests that, you know, after a certain age or after a certain wage, the income effect starts playing in and you would want to work less, or even just simply by the fact that an elderly or someone that's older cannot work for so long, so naturally their income decreases. So let's just take that for example. So there's two ways of doing it. The first way is not an accurate way and not the best way, but it's still a method and it's not recommended to use in regression. I can't remember the reason why, but there is a certain reason why we don't use it, but I'll still show you. So if you want to say like h², right, we're going to estimate that it's a concave relationship. So we can make a new variable, which is gen, and then let's call this something appropriate like h², hsq. And then you basically, what you do is equal, because you're just trying to assign something, and then age asterisk, which is shift 8 on my keyboard, times age. That basically creates another variable, which is just basically h². And then what you can do is basically run a regression with it. Age, h², and while c. And here, yeah, as predicted, as your age increases after a certain point, then you get, you know, you get a decrease in income instead of an increase in income. And, you know, the R-squared instantly increased 0.07, which is still kind of bad because it's, you know, not over 20-30%, but it's better than 5%. 7% is better than 5% when we're looking at the R-squared. We can also look at the adjusted R-squared. That's also increased significantly. So that's a good sign. However, that's not like the best way of adding h² to regression. There are actually two other ways, which are basically the same thing. So let me just drop h² because we don't want that because that's stinky. And we will do it the other two ways. So the other ways is you don't even need to create an actual variable. You can just do it by using the hashtag or the hash key on your keyboard within the regression. So let me show you. So we do regress income nk age, and then we do c.age hashtag c.age. So essentially what the c means is it tells Stata that this variable that we are putting after is a continuous variable, and the continuous variable is basically numbers. It's not a categorical variable. A categorical variable is something like smoke and does smoke. So 0 would be not smoke, 1 would be smoke, something like that. But age is just a number. It can be any number. There's no set limit to what number it could be. So that's why it's a continuous variable. And the hashtag just means multiply, and then c.age means times it by itself. So if you want to do an interaction term, which I won't get into because it'd be too complicated, you could just do like c. I don't know, whather, and that'll give you an interaction term. But we want h², so we'll keep it as that, and then we'll do c, because that was in our previous regression. And essentially we get basically the same thing. Yeah, it's identical in this case. I'm not sure why people don't use this one, but we'll just go with that for the time being. But yeah, you get basically your normal age and then your normal h², and that's basically it. And then the final way of doing it is basically the same as before, but I'll show you again. So this is basically just the shorter or quicker method of what we just did above. But instead of putting one hashtag, you put two hashtags and get rid of the age beforehand. And what this does is it shows you age and age squared. So I'll show you again by pressing enter. And yeah, as you can see, it's identical. You can pause the video here and pause the video here, and you can see that they are exactly the same. There's no difference between them. So basically, one's with double hashtag without the age, and one's with age and just one hashtag, but they give you the same result. So this was just a mini crash course on regression. Hopefully it helps. And yeah, if you're on my course, good luck. And yeah, if you want any more like tutorials, just let me know in the comments below. But yeah, hopefully this helped, and I'll see you guys later.